So hello everyone, I'm Norman Wahlberger. We're at the University of New South Wales. And today we're going to start a course in differential geometry. It's going to be an elementary or beginner's course in differential geometry, but we're also going to be looking at some advanced things along the way. All right, so the topics that we're going to cover include roughly the following, although there will probably be some other things as well. We're going to look at classical curves and surfaces. We'll talk about Frenet-Serre frames associated to curves in space. We'll look at the idea of osculating conics, the idea of curvature of curves and surfaces. We'll talk about Gauss's theorema egregium, which is Gauss's sort of celebrated theorem on the curvature of surfaces. We'll talk about the first and second fundamental forms of a surface, the so-called shape operator. We'll have a look at minimal surfaces and mean curvature, probably get some soap solutions and make some soap bubbles. We'll have a look at rule surfaces and developable surfaces, which are very important in manufacturing applications. We'll look at geodesics and the Gauss-Bonnet theorem. And then there'll be also some material on topology, basic ideas of continuity, topological spaces, indexes of curves, classification of surfaces, and the Euler characteristic. So there's some natural connection between differential geometry and algebraic topology. Okay, so what's my orientation? This is going to be a classical course in one way, in that the topics are rather classical, but it's going to be rather novel in another way, in that the approach that I'm going to take is maybe innovative and rather modern to a number of subjects. So we're now, just at this period in time, experiencing a whole bunch of new ideas in geometry and perhaps also in calculus. And these new ideas are going to help us understand differential geometry in perhaps some interesting new ways. So my point of view, roughly, is oriented towards the following ideas. So I prefer rational or algebraic techniques or objects to transcendental ones. We're going to occasionally not shy away from classical geometry, so we're going to use some classical geometry. In particular, we're going to perhaps have a little role for projective geometry, and especially talk about quadrics. It's going to be very important for us. And along the way, we're going to talk about quadratic forms and sort of we'll adopt the language of rational trigonometry in some cases, which helps us understand a few things. I'm also going to encourage the use of GeoGebra for visualization. This is a dynamical geometry package that allows us to visualize planar situations, and it's quite helpful, and we're going to be using that. We're also going to be sticking to 2D and 3D mostly, where we are in the realm of practical experience, the world in which we live in. But we have a view, nevertheless, to physics. So, in particular, about 100 years ago now, Albert Einstein introduced the special theory of relativity and then the general theory of relativity. And this was really a remarkable watershed in the history of science. And differential geometry has a lot to do with his work. So although we're not going to be really getting to a full understanding at all of general relativity, nevertheless, we're kind of oriented in that direction. And so we're interested in understanding general relativity ultimately. All right, so that's the basic framework that we're going to adopt. Today, I'm going to have a look at some classical curves, going back to antiquity. All right, so the study of curves took off in the 17th century with the work of Huygens, Newton, then Euler, Monge, then taken up by Cauchy, Gauss, and so on. But earlier, back in ancient Greece, there were lots of interest in classical curves. So there's some classical curves. The simplest one, of course, I suppose, is just the straight line. But then after that, we get the conic sections. And these are the curves that we get when we take a cone and we slice the cone with various planes. We slice the cone in this kind of way, we get an ellipse. If we slice the cone with a plane perhaps more up and down, then we get a hyperbola. And if we slice the cone with a plane which is parallel to one of the generators, say parallel to this one, then we get a parabola. All right, so we have three different classical conic sections: the ellipse, the hyperbola, and sort of halfway in between them, the parabola. So these were named by Apollonius. And there's some other sort of degenerate conic sections that you get when, for example, if you slice the cone with a plane that's exactly in the board, then you'll get two crossing lines. Or if you happen to slice the plane just through that point there, well, then you can just pick up one point. Or you can actually just get a single line by slicing it like this. All right, so these conic sections are going to be important for us. And so, of course, I'll just remind you that there's some alternate points of view towards the conic sections. So we can also think of them metrically. They also have metrical definitions. And typically that's involving a point and a line, and a point x somewhere. And then we look at the relationship between the distance between the focus F and the point x, and the vertical distance from the point to the line. But in fact, I prefer to think rationally, so I'm going to use quadrants instead of distance. So quadrants is just the square of the distance. All right, and that allows me to say this in a more algebraically simple way. So the point is that if we look at the condition that the quadrants of x and f equals the quadrants between x and the line, then that's the condition of a parabola. So that would be something like this, perhaps. So here the ratio between the quadrants to the focus and the quadrants to the line is some number epsilon less than 1. In that case, we get an ellipse. And if we look at the case when the constant is bigger than 1, we get a hyperbola. All right, and then we all know that this is called the focus of the conic, and this is called the directrix. And this was known back in antiquity. But what's not so clear, and what wasn't really understood until the 19th century, was the relationship between these two definitions. So if you have a cone, and we take some plane, let's say that it's cutting out an ellipse, Then where is the focus? Actually, there are two foci for an ellipse. So there's a foci here, but there's also another foci on this side and another directrix on this side. So we can naturally ask, where are the foci for this ellipse if the ellipse is cut out from a cone? And that was answered only in the 19th century by a French mathematician, Danelin, who had the following solution. He said, take a little sphere and place a little sphere in the cone. Okay, so it's just sitting there in the cone, like a blob of ice cream. And then expand that little sphere so that it stays inside the cone. Make it grow, so it grows until eventually it just hits its head against the plane of the ellipse. Okay, at some point it just touches the plane, and where it touches is one of the foci. And to get the other foci, what we do is we start off with a very big sphere that's sitting on the cone way above the ellipse, and we shrink it. And as we shrink it, it comes down, 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 until eventually it hits the plane of the ellipse from on top. When it does so, it will touch the plane in the second foci. Now you might also ask, where are the directrices in this story? So it turns out that if you take the equator of this sphere, that's a plane. That plane cuts the plane of the ellipse in a line. That line is a directrix. And similarly, if you take the equator of the sphere on top, it has a plane. And when you intersect that plane again with the plane of the ellipse, you get another line. And that's the other directrix on the other side. Okay, there are a few other incarnations. There's quite a few other incarnations of the conics. For example, another way of getting an ellipse is to take a circle and apply an affine transformation. If we stretch the plane in one direction more than the other, then we can get a circle, an ellipse. There's another connection with complex function theory. So I remind you that in the complex plane, the cosh function in terms of x plus iy is equal to cosh x cosh iy plus sinh x sinh iy. And that can be rewritten as cosh x times cosine y plus I times sinh x sine y. And I also remind you that cosh z can also be written as e to the z plus e to the minus z over 2. So it turns out that the level curves of this function give ellipses. So if we're in the complex plane, so maybe I should say it. If the real part of z equals x is fixed, let me say it this way. If the real part of z is x equals fixed, then y goes to x plus iy, which is cosh of x plus iy, will trace out x squared over cosh squared x plus y squared over sine squared x equals 1. So that's an ellipse with foci 1, 0 and minus 1, 0. So there's a natural connection with the cosh function as well. All right, so that's just a little bit of an introduction to these conic sections. In the 17th century, the geometry of the Greeks was perhaps somewhat replaced by the analytic geometry of Descartes. And what happened there is that it's a whole new dimension. The analytic geometry of Descartes allowed us to understand that conics have an algebraic description in terms of, well, first we should say that a line is something of the form ax plus by plus c equals 0. So a linear equation in x and y is, of course, a line. And a conic is then just a degree 2 curve. So it's a curve that has the general form, say, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So this algebraic form allowed Descartes to sort of organize all the conics into sort of one big family, just viewed algebraically. Okay, so the Greeks had other ways of creating curves. They had a method of creating derived curves, where we start with a certain curve, or sometimes a pair of curves, and we perform some operation to get a new curve. So an example of this was the conchoid construction of Nicomedes around 200 BC. And the picture is we have a curve C, let's say, and then we choose a point O, and then we choose some variable line through O, and it cuts the curve in some point, let's say Q. And then we go in equal separation from Q on either side. So we go maybe K in that direction to a point P1, and also K in this direction to a point P2. And then as Q varies, P1 and P2 are going to trace, in some sense, some kind of parallel curves to C from the point of view of O. Right. So we're going to get these two new curves sort of following C roughly, but maybe not exactly, depending on the position of the lines. And these are called conchoids of the original curve. So the locus of P1 and P2, where, say, the quadrants between P1 and Q equals the quadrants between P2 and Q equals, say, capital K, is a conchoid of the original curve C with respect to the point O. Okay, and I hope we're familiar with the term locus. So locus means the path generated by something. Okay, it's the path generated by something. So in this case, the path generated, well, we have actually 2 points now creating a pair of curves.
So is this simply speaking conchoid just a parallel curve?
Well, it's not exactly parallel because it's parallel from the point of view of O. It's not that all these lines are exactly parallel. They're all going through this fixed point O. So by the time we get over here, for example, we still have to go K in this direction and K in this direction. So it would be something more like this, maybe. A similar kind of construction is that of a cissoid. I'm not sure if I'm pronouncing that right. And that was introduced by Diocles, also around 200 BC. And he introduced it, in fact, for a very famous reason. There's a famous problem called the doubling of the cube problem. Okay? So the doubling of the cube problem is you have a cube of side 1. And you want to construct, by ruler and compass, a bigger cube, which has exactly twice the volume. Okay, so we want to construct a bigger cube which has exactly twice the volume of the original one. So we know that the volume of a cube is the cube of the side lengths. So we really want this thing here to be cubed root of 2. That would ensure that the volume is actually 2. So the question is ultimately, how do you construct this number, cubed root of 2, by ruler and compass constructions? Well, nowadays we know that that's not possible. Okay, but the ancient Greeks didn't know that, and they tried to find some ways of doing that. And Diocles did not find a ruler and construction way, but he introduced this other curve that helped him to solve the problem in a slightly different direction. Okay, this cissoid construction, here's the general one. So it starts off with two curves. So suppose we have a curve C1 and a curve C2. They don't have to be parallel or anything. And again, we have some point O. We draw again lines through O, meeting the two curves in 2 points. And then what we do is we take this vector and we translate it back to O. And so we take this separation and translate it back to O, getting a point there. And as we do that for various lines through O, we get some other curve, and that's called the cissoid of C1 and C2. Now, there's actually a famous cissoid, which is the following. So if we start in the xy plane, and we have a circle, say going up to the point 1, and we have a line that's tangent to that circle through there. This is the line y equals 1. This is a circle centered at a half here. Then the cissoid of these two curves is particularly famous, and it's called the cissoid of Diocles. So what does that look like? Well, so with respect to which point? Well, with respect to this point O here. There's the point O. Okay. So what we're doing is we're taking lines through O, seeing where they meet. There are two curves, the circle and the line, and then taking this vector and translating it down here. And I hope you can see that as the line approaches here, right here the two curves coincide, so we're actually going to be right here. So this cissoid looks like something like this. This is sometimes called the cissoid of Diocles. All right, so here's a problem for you. Find a rational parametrization of this curve, of the cissoid, of Diocles, and give its algebraic equation in terms of x and y. I also want you to sketch it on GeoGebra. All right, there's some other famous constructions. There's the evolute and the involute constructions. I'm not going to say too much about that. Question?
Sorry, what is the rational parameterization?
Okay, rational parameterization means, so x of t, let's say the parameter is t. So x of t and y of t. I want this expression to be a rational function in t. Polynomial over polynomial. No cosines or transcendental business. Rational functions. Of t. All right, so for the evolute and involutes of a curve, it's a very important part of our story, but I hope that you will all have a look at Math History 16, which is a history short review of differential geometry. And in this video, I talk a fair amount about evolutes and involutes. Okay, so just very quickly, if you have some curve C, then an involute is what you get when you unravel a string that's tied to it. So if we imagine having a string that's tied to the curve and then we unravel it at some point, keeping it tight, keeping it sort of tangent like this, then the curve that we get here is an involute of C. And we should say an involute because there are lots of them. If we started by unraveling at some other point here, we would get some other involute. Okay, these were introduced by Huygens in the 17th century. And then the somehow dual construction to that is the evolute, where you have a curve and you take tangents and then you take normals to the tangents, and then you see where adjacent or very close normals meet. So there's a point P and there's a point Q. Then the normal to Q and the normal to P will meet somewhere. And in the limit, as Q approaches P, that limiting position of the intersection of the normals is a point that depends on P. So now if you change P and you do the same thing somewhere else, you're going to get some curve that traces out the centers of curvature of the original curve. It's called the evolute of C. That's C. And it's really the locus of centers of curvature. Okay, so that's an important construction historically. But there are a few other ones too. Okay, so another interesting way of getting new curves is the idea of a pedal curve. All right, so here we have some curve C, and we have some point O again. And what we do is we take some variable point on C and look at the tangent to the curve through that variable point. And then we drop a perpendicular from O onto the tangent, okay, giving us a new point. Well, let's choose another point. Let's say the point happened to be there. Its tangent would be here. And then dropping a perpendicular, we would get this point here. So the feet of all the perpendiculars from O to various tangents of the curve, that's called a pedal curve. Get some curve called the pedal curve of C, again with respect to the point O. This turned out to be quite an important concept for Newton in his study of planetary motion and Kepler's laws. There's an interesting example of this. If you take a parabola, there's a parabola, and you take the point in question to be the vertex of the parabola, then the pedal curve of the parabola with respect to the vertex is, so here's a point, there's a tangent, there would be a perpendicular point. My diagram's not that good. Up here, some other perpendicular point. Okay, what you're going to get is a curve like this. It's exactly a cissoid of Diocles. So the pedal curve of a parabola with respect to its vertex is the cissoid of Diocles. So in the 17th century, when Newton introduced the laws of motion and the calculus was being rolled out, people got very excited about the possibility of using calculus to understand motion of all kinds of things. And so motion and mechanics became important drivers of mathematics and also of curves. So there's a whole new family of constructions, which are generally under the name of roulettes, where one curve rolls on another without slipping. And then any fixed point describes what's called a roulette. So this is a very general kind of story. I suppose 1L. So you have some curve, and on it you have some other curve. Maybe it's an ellipse, for example. And on this ellipse you have some special point. And as the ellipse rolls on the ellipse is just rolling without slipping on the curve C. Then you trace what happens to this point, wherever it is. And that's called that curve is called a roulette. A cycloid is an example, right? That's a very famous example. So, for example, a cycloid, where a relatively simple situation where you just have a circle rolling on a line, and then you get some curve like this. Circles rolling on the line, and that's a cycloid. There are other examples. If you have a circle rolling on top of a circle, like this, you get some kind of thing like this. That's sometimes called an epicycle. Or you could have a circle rolling inside a circle. When we were kids, there was this toy that children had called spirogram or something like that, with these little gears, and you roll these gears around these little wheels, making all kinds of pretty patterns. Exactly this kind of idea, where you have these little wheels attached to each other with cogs, and you can move them around. So here, this is sometimes called a hypocycle. And if the radii are suitably chosen, and you arrange so that you're going around so it closes up after going 3 times. That's an interesting special case. That's called a deltoid. But we don't have to have circles rolling on circles. We can have any kind of curves rolling on any other curves. So another interesting example is if you have a parabola which rolls on a congruent parabola. Okay, so here are 2 congruent parabolas. We imagine this one might be fixed, and this top one is allowed to roll on the other one. So after a little while, it might be up like this. Something like that. Then if we take the locus, say, of this vertex here, and see, it's not very clear what I'm doing here, but if you do this a little bit more accurately, then you find that, lo and behold, you get, once again, a cissoid of Diocles. That same curve that you're finding the parameterization for in this equation in that problem. All right, so a lot of these curves are what's called transcendental curves. They are curves that involve non-algebraic aspects. They're quite different from the conics because the conics have an algebraic equation in terms of x and y. You can write down the equation for them. These ones you need cosines and sines or perhaps some other kinds of functions to describe them. Naturally, mathematicians were also interested in, well, what about the algebraic curves? What happens when you go beyond the conics, the degree 2 curves? That's a very natural question, right? Once you've understood conics, and that's reasonably easy to do, Descartes thought that he could prove everything that the ancient Greeks knew about conics just from his formulas. Apollonius had hundreds of results about conics. Descartes was confident that he could prove all of them just by maybe making algebraic manipulations instead of any kind of geometry like Apollonius was doing. So naturally, after the conics was kind of exhausted by the 17th century mathematicians, they naturally turned their attention to the next degree, the cubics. Okay? So the cubics are a whole new world. Cubic curves. So there's much to be said about cubics, and we are going to have a look at some aspects of them in this course. So there's, first of all, cubic functions. This is sort of a baby kind of version where you start with y equals a function, a general cubic. Okay, we all know what the graph looks of these. They are going up and down and then up again. Unless the sign is changed, in which case they go down and then they go up and then they go down again. Okay? But more or less any cubic looks like this. If it's a cubic of this form. But it's important to understand that this is a very limited kind of a cubic. Right? The general cubic is much more complicated. The general cubic has the equation ax cubed plus bx squared y plus cxy squared plus dy cubed. Those are all the degree 3 terms. Then there will be degree 2 terms, ex squared plus fxy plus gy squared. And then there will be linear terms, hx plus iy. And then typically a constant term, j equals 0. So that's your general cubic. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 parameters in it. So it's it's some kind of 9-dimensional space of cubics. I say 9-dimensional because you can always multiply this equation by a scalar, and it's really the same cubic. So there's 1 degree of freedom there that's scaled. All right, so there's lots of cubics, and the natural question is, what do they look like? It's a much richer story than the cubic functions. So for example, one kind of cubic that you can get, a very simple cubic, is just to take the product of 3 lines. That's an example of a cubic. Just take the equation of one line, multiply by the equation of the other line, multiply by the equation of the third line. You're going to get a degree 3 curve, and its set of points is going to look like that. Now, if you take that particular cubic and you modify the terms just a little bit, Okay? Then it's going to perturb, and it's no longer going to be a product of 3 lines. Typically what happens is something like this. You will get a blob inside here like this, and then these branches sort of become curves that are sort of asymptotic, roughly. So you may get something like that. Right? So that's a kind of a cubic curve. But there are many others, and Newton, no less, was naturally interested in classifying cubic curves. He saw this as an important thing that one should do. One should classify cubics. Right? And in fact, it's something that everyone who's doing mathematics, it should occur to you. After you've done conics, you should ask, well, what about cubics? Can we classify them? Is there anything like ellipse, parabola, hyperbola, that kind of thing? Well, it's much more complicated. He classified them into some 80-some different types. He had a few that were missing. The story is quite a long story. We're not going to go into it, but these days there's some sort of canonical forms. If we make something a little bit more general, y squared equals ax cubed plus bx plus c. So more or less with a suitable transformation of variables, and actually we need a projective change of variables, you can cook up any cubic to be sort of this form. And then there are various possibilities. So one possibility is something like this. Another possibility is something like this. Another possibility is something like this.
Is it this called the elliptic curve?
Well, some of these are elliptic curves. So this is not. This is an elliptic curve. This kind of curve has a singularity. There's a point of non-differentiability there. And this curve also has a non-differentiability. So these curves here are somewhat different from this one, which is non-singular. Okay? So non-singular cubics are called elliptic curves. So an important problem that's related to these cubics is how to parameterize them. How do you describe the points on a cubic like this? It was known since the ancient Greeks that you could parameterize conics. Any conic can be parameterized in the sense that you can find a rational function to parameterize a conic. It turns out that not all cubics can be parameterized. So the story with cubics is considerably more complicated than with conics. So not all cubics can be parameterized. Okay, so that's probably a good place for us to stop. The next lecture, we're going to delve a little bit more into this issue of parameterizing cubics. We're going to have a look a little bit more at cubics, a whole new world there. And sometime in between then, I'll post that video on GeoGebra. So I'll see you then.